Radian measure. This is an alternative way to measuring angles. Instead of using degrees, we use radians, where radian is defined as the angle subtended at the center of the circle by an arc whose length is equal to the radius of the circle. Well, what does this mean? We can look at it in two ways. With the point moving through a given angle, we can see it as the point moving along the arc, or we can see it as a rotation. If you have a look at this, the way the eye rotates, the angle through which the watching eyes turn. So it's the angle through which the eyes turn, the angle through which the distance through which the point has moved. Now, this is in pre-calculus, and calculus is a mathematics of motion, of rate of change, so it needs to work in radians. Further to this, the angle in radians is equal to the arc length divided by the radius length. So let's have a look at a relationship between radians and degrees. There's an angle of 360 degrees. There's an arc length of 2 pi r, being the circumference of a circle. Now, the angle is equal to the arc length divided by the radius length. So if I take this arc length of 2 pi r and divide by r, I should get 360 degrees. Which means, therefore, that 360 is equal to 2 pi radians. And easier, 180 degrees is pi radians. Now, you've probably spent 12 years at school using degrees and having palpitations now that suddenly you have to use a new system, because this system is used far more at the universities because of the calculus. But you can still convert between the two and think in degrees until you get used to the idea. Let's consider a conversion. N degrees to radians. Well, there's the n degrees. Now all we have to do is multiply by what is essentially 180 degrees over 180 degrees, but we're putting the pi equivalent to 180 on top and the 180 degrees below to allow the degrees to cancel. So in fact, 90 degrees, we take 90 and multiply by pi over 180. 180 over 180. And we get pi over 2. Pi divided by 2, which we refer to as pi by 2. 30 degrees, well, into there giving 6, so pi by 6. 150 degrees, 30 cancels into both, 5, 6, so 5 pi by 6. This one gives you a decimal, another decimal with a negative angle, and another decimal. 210, well, 30 cancels into both, so 7, 6, 7 pi by 6. 270 and 180, 90 cancels into both, so 3 pi by 2. And negative 120 degrees, 60 into both, 2, 3, so negative 2 over 3. Note that radians, being a ratio, they aren't really a unit. So you don't have to put radians there. That's why this is faded and in brackets. But if you want to indicate that it's radians, then you can always put RAD, the abbreviation, or superscript C for circular measure, and those are the symbols for radians. Then K radians, 2 degrees, we do much the same system, but instead of multiplying by pi over 180, we multiply by 180 over pi. Remember, we're really multiplying by 1, because 180 and pi mean the same thing. Pi radians is 180 degrees. So pi by 3, we take it, multiply by 180 over pi. Give you 60 degrees, because the pi's cancel. 3 pi by 4, we multiply by 180 over pi, the pi's cancel. We end up with 3/4 of 180, 135. But remembering that pi is really 180 degrees, why don't we go straight off there and put pi as 180 degrees there, so we get our 60, and 180 degrees there, and we can multiply it out immediately. And we're going to do the same thing here, 180 degrees there, and it simplifies to that angle. Some practice. Here's some conversions to radians. Remember, you just multiply each by pi by 180 to get it to radians. And then converting to degrees, in these cases, you just multiply by 180 over pi. You see, you need to cancel the pi out, so therefore you multiply by 180 over pi, 180 and pi being equivalent, so you're really multiplying by 1. Let's look at one use of radians, an arc length, finding the length of the arc of a circle. So there's the arc length. We denote it by S. Well, by definition, the arc length over the radius gives you the angle in radians, which means then that we can write that arc length is we multiply up by the r times theta. Theta being radians, not degrees. So there's a formula. So here are some to try. Try them yourself. In this first case, r theta, so we just multiply by 7. And we can leave our answer as that. Multiply by 7. Here it is. Here we need to convert that to radians first. So I multiply by pi over 180 and multiply by 7. Convert to radians first, so we multiply by pi over 180 and multiply by 7. And that's already radians, so just multiply by 7. We don't need the negative there because this is the length of a line. Sector area. A sector is like a slice of cake, that section of the circle. Now we might ask, well, what fraction of this whole circle is that sector? Well, the degrees or the radians can indicate it to us, these angles. That angle is the same fraction of the whole lot as this sector is of the whole circle. So when we talk about the area of the indicated sector is the fraction theta over 2 pi of the area of the circle, because theta is the angle and 2 pi is the full distance around in radians. And the area of the circle is pi r squared. So we can multiply them, and that gives us a formula for the area of the sector. Let's do some examples. Find the arc length, angle pi by 3, radius 4. Well, that's straight off. Do each of these first, and then I'll go through the answers. So in this case, S is r theta. There's r, there's theta. So we simply multiply 4 pi by 3. Next one, we have arc AB, center O, radius r, subtangent angle of theta at the center, and this is in radians. The perimeter is p centimeters. Express r in terms of theta. Well, we're going to use that same formula. We have the theta, so that's fine. We have the R, so we just need S. Well, we have the full perimeter is P, and we know that's R and that's R. So surely that is what's left. So therefore S is equal to P minus 2R. Now we can substitute into our formula, and we can solve for R. All R's on one side, common factor, divide. So now we're given the area of a circle. Find the angle subtended at the center of the circle by that arc. Now consider this, and then you can try it. We have to find the angle. We know the arc length, and we need to know the radius. Well, knowing the area, we can find the radius. Try it yourself first. So the area of a circle is pi r squared. So therefore pi r squared equals 450. That we can solve to give us the value of r. Now knowing r, we know the r there, we know the s, so we can find the angle theta. And there it is in radians. So now we're given the area of a sector. There's the formula for the area of a sector. Calculate the value of r. Straight substitution. We have 0,8 is theta. We have 28,9 is your a. So we can substitute into the equation. And we're going to solve for r. (8,5). So now we have a plot of land, the shape of a sector, circle radius 55, and 176 meters of fencing is required along the whole lot. And we want to know the area of the plot. Well, the area is half r squared theta. So we need to know theta. We have r, and that will give us the area. But we have to find theta first. That we can do using this first formula here, S equals r theta, if we know S, which you can work out because the perimeter of the fencing is 176, and we know that's 55, and that is. Try it first. Okay. So AB is going to be equal to that 176 less twice those 55s, giving 66. So we now know the arc length. We know the arc. We know the radius, which means we can find the angle. So there is our angle in radians. Actually easier to work with than degrees. Now we know our theta, we know r, so we can find the area. There's the area of our plot. Now, show that the area of the shaded segment is half r squared into theta minus sine theta. These always look pretty daunting because of it having in the variables, but these are usually easier in fact. Area of the shaded segment. So how do we get that? Think about that first and try it yourself. If you're stuck at this stage, that shaded section will be the sector area minus the triangle's area. Now sector area, we have a formula for it. Triangle area, we have trigonometry. Do you remember half AB sine C is your area formula for the area of a triangle? So, area equals sector AOB, the whole sector, minus triangle AOB. In sector AOB, there it is there, triangle AOB is sine rule. Yeah, so half r squared theta minus half AB sine O. Substituting in then, we know that A and B are both r squared and O is theta. And now it's just a case of factorizing to give us our required answer.